Hey, I wanted to send you this little video. I want to make sure we have a concept right here. It's important. It's going to be brief. And as an example here, remember the bowl problem. There was a bowl, you started a marble up here at this top, and this little jagged part that I put the jagged lines on is friction, so it's rolling without slipping here. It gets to the bottom, and then it's without friction. Without friction over here, my little swirly lines, I don't know. And so the question is, how far up does it slide before it comes to the stop? H. We'll find H here. Okay, so the way this works is the ball has a certain amount of potential energy to start off with, and it rolls without slipping till it gets down here at the bottom. Okay, and at that point, all this potential energy, mgh, is transformed into kinetic energy, 1/2 mv squared, plus angular rotational kinetic energy, 1/2 I omega squared. Okay, and you know how to do that. We know how to figure that out. You go find the velocity, and you've got that. But then it hits the part where there's no friction. Okay, so it is spinning, it is rotating. As it hits the part with no friction and starts up, there's nothing to stop it from rotating. It's still rotating. Therefore, the rotational kinetic energy here is the same as the rotational kinetic energy here. It's still rotating when it comes to a stop up here, when the translational velocity comes to stop. Okay, so that makes the formula pretty easy. 1/2 mv, VB is V of the bottom squared, the velocity down here, translational velocity, 1/2 mv squared is equal to 1/2 m velocity at the top squared plus mgh right here. Okay, so that's a very, in the previous part you've solved for V, the m's cancel out, so it's pretty easy to figure out the height at that point. Okay, the key is this thing is rolling, spinning when it gets down the bottom, and it keeps on spinning. No change in rotational kinetic energy from here on up. That's a similar situation to the tire coming off the cliff. It's rotating along the cliff, and then it comes to the edge of the cliff and drops off. Out here in the air, it's still rotating. It's still rotating, and when it hits the bottom, it's still rotating at the same speed. There is no change in rotational kinetic energy. Now we write the formula for that: 1/2 m velocity of the top squared plus 1/2 I omega squared plus mgh, the potential energy, is equal to 1/2 velocity of the bottom squared plus the rotational kinetic energy at the bottom. Well, okay, cool. Well, it's still rotating at the same speed. There's no change in these rotational kinetic energies, so they cancel out. All right, and the m's cancel out, and every term's got an m, and it becomes very easy. Velocity at the top squared plus gh, because the masses are canceled out, is equal to the velocity of the bottom squared. Okay, so I just want to point out to you about how the energy changes from potential to kinetic plus rotational, and it may or may not be rotating, so there you go. You have to take that aboard. That's all I wanted.